Okay, folks, I'd like to go ahead and cover the very first question in section 4.2 in our in-class work that says we'll be done together. So we're asked in this question to find the critical numbers of this given function. Well, I'd argue that you don't know how to do this question if you don't know what a critical number is. So let's review our section 4.1 notes from the other day. We're in 4.2 now. If you pull up your 4.1 notes, so this is our 4.1 notes in class work. And if you look at number 37, we defined a critical number there. We said we're only going to consider interior points on the domain, and we will say that that interior point is called a critical number if either the derivative is equal to 0 there or the derivative doesn't exist there. Okay? So critical numbers are a term that we use to define places where the derivative is 0 or the derivative does not exist. We're going to call that a critical number provided that point is an interior point in the domain. Let's return to our question. So for this function here, we want to find those critical numbers of this given function. Well, first of all, because we only want to consider points interior to the domain, we better identify what the domain of this function is. So pause the video, think for a minute, what is the domain of this function? So it turns out that the domain of this function is all real numbers, from minus infinity to infinity. Why is that? Well, if you look at the operations that we're doing in here, we're doing some subtraction, that works for all numbers. We're doing some multiplication, I'm multiplying this factor, that works for all real numbers. I'm squaring, because of that to the second power, so I'm squaring, that works for all numbers. And I'm taking the cube root, and I can take the cube root of all numbers. Just as a reminder, x to the 2/3 could be thought of as the cube root of x, quantity squared. And I can take the cube root of all numbers, and I can square all numbers. So that's why this expression is defined for all real numbers. Now be careful here, if this had been x to the 3/2, that would have been a different story because we would have had a square root. Okay, so let's return to our question. So we've identified the domain, and now we're looking for our critical numbers, so let's go ahead and find f prime of x. So we're going to compute the derivative of this. We're going to have to do the product rule, so here's our first, times the derivative of the second factor. Well, the derivative of the second factor, 5 minus x, is -1, plus the second times the derivative of the first factor, which would be 2/3 x, and then I subtract 1 from 2/3, so I get -1/3. So there's the derivative of this function. But because I'm going to be doing more work with this derivative, namely I'm going to know where this derivative is 0 or undefined, I'd like to go ahead and write it as a single fraction. To be honest, that's the hardest part about these problems. Oftentimes you have to rewrite them as a single fraction to identify the places where the derivative is 0 or the derivative is undefined. So let's go ahead and clean this up a little bit. I'd like to rewrite this as minus x to the 2/3. And then for this expression here, I'm going to go ahead and rewrite the x to the -1/3. I'm going to put that factor in the denominator here. So it turns out I can rewrite this expression as 2 times 5 minus x all over 3x to the 1/3. Let's double check that that makes sense to you. Remember, I can rewrite this expression, x to the -1/3, I can rewrite that as 1 over x to the 1/3. Okay? And so then I would have 2/3 times 1 over x to the 1/3, and all times this factor here, which I could think of as 5 minus x over 1. And if I write the numerator as a single expression and the denominator as a single expression, that's how I end up with that fraction. Folks, if you had trouble on that, please let me know. Okay, let me clean that up a little bit. All right, so remember, my goal here is to rewrite this expression as a single fraction. Okay. So let's see what we can do here. For me to be able to combine these two terms, I need a common denominator. My common denominator is going to be 3x to the 1/3. So I'll take negative x to the 2/3, multiply it by 3x to the 1/3 over 3x to the 1/3, plus, and then I'll just recopy this expression here. So folks, don't let your eyes glaze over. All I'm doing is I need to combine these two expressions as a fraction, so this expression needs to be written in terms of the common denominator, 3x to the 1/3. So I'm multiplying by that common denominator over itself. When I do so, I end up with, well, negative 3. Now, I'll write this out. This will be 3x to the 2/3 times 1/3, which I then add the powers together. But what is 2/3 plus 1/3? Well, that's 3/3. And how else can I write 3/3? I can write it as to the first power. Or if I like, I cannot write it at all. So when I multiply the numerators together, I just get negative 3x. In the denominator, though, I've got the 3x to the 1/3. And for this fraction over here, on this right-hand side, I'm simply going to distribute this 2 to both terms. So that gives me plus 10 minus 2x all over 3x to the 1/3. And now I'm in a position to actually combine these fractions together. And I'm left with 10 minus 5x all over 3x to the 1/3. So all of this work was to rewrite the derivative as a single fraction. Whew, let's get caught up. What are we trying to do here? We're trying to find the critical numbers of this function. Well, to do so, we went ahead and said, well, we need to find the interior points on the domain where the derivative is either 0 or undefined. Well, we found the derivative. We actually found that in just one quick calculus step, and then we had to do a bunch of algebra to write this as a single fraction. But now that we've written it as a single fraction, it's easy to see that f prime of x equals 0. Where? Well, when is a fraction equal to 0? It's equal to 0 if its numerator is equal to 0. That is, I can just set the numerator of this equal to 0, and that happens when x is equal to negative 2. So that makes negative 2 a critical number of this function. Now careful, folks. One thing I'm checking, even though it doesn't matter in this problem, I'm ensuring that x equals negative 2 is an interior point of our domain. But what did we say our domain was? We said our domain was all real numbers, so we're okay there. Okay. All right, now let's go ahead and, so we've answered the question, where is the derivative 0? Where is f prime of x undefined? So let me just, this was a question, where is f prime of x equal to 0? And where is f prime of x undefined? Well, that's a little bit easier to see. Here's our derivative. And this was our f prime of x. Here's our derivative. Where is this expression undefined? Well, it's undefined if the denominator is 0, and that would happen if I plugged in a 0 for x. So that it's undefined at x equals 0. So I'm a little bit out of room here, folks, but here I'm ready to say what the critical numbers are. Here's my final answer. The critical numbers are x equals negative 2 and x equals 0. And something to keep in mind, and this is a little bit confusing, something to keep in mind is that the reason why x equals negative 2 is a critical number is because that's where the first derivative was 0. And the reason why x equals 0 is a critical number is because that's where the derivative is undefined. So they're both critical numbers, but they're critical numbers for two different reasons. Finally, the last thing to emphasize is notice that both of these numbers, negative 2 and 0, were within the domain of f. If they were not in the domain, if they were either outside the domain or on the boundary of the domain, then we would not count them as critical numbers. Okay, let me zoom out so you can get a better look at that, and we'll stop the video there. Please let me know if you have any questions.